In this video tutorial, we're going to use something called the finite difference method in order to approximate the temperature distribution on this given object. Now, before we do that, it's important to understand where the equations come from that we're going to be solving here. So I've produced a relatively brief derivation of the equation that we're going to use, and this can be found on the Engineers Academy study platform. I'm going to discuss it very briefly here, just so you can understand where the equations are coming from that we're going to apply to this problem. So one of the equations that can be used to solve various different problems in engineering is something called the Laplace equation. And what we're going to be starting with here is the Laplace equation for heat transfer problems. Now, the issue that we face here is that we can't apply the Laplace equation directly. Here we have the Laplace equation, delta squared t over delta x squared plus delta squared t over delta y squared equals 0. But what we can use is a finite difference approximation to this particular Laplace equation. And the way that we do that is first of all to generate two different equations, one for the first term in our Laplace equation and one for the second term. So the two equations that we see there are called the finite difference approximation of those terms on the left-hand side. Essentially what we're doing, as we mentioned in the previous video, is we're trying to find out information about one location based on information we have from neighbouring locations or neighbouring nodes. So here we have the temperature at a given point, and here we have the temperature at a neighbouring point in the x direction, and here we have the temperature at a neighbouring point in the opposite direction. We see the same repeated for the second equation, except y is replaced with x, and we see that we have the same term in the centre there, the temperature at a given point, xi, yj, and we see the temperature at the two neighbouring points neighbouring in the y direction, so above and below our central point, whereas the previous equation had the temperatures to the left and right of our neighbouring point. Now, where this becomes useful is when we simplify and rearrange that equation. Now, as I mentioned, I'm not going to go through this full derivation, but what we end up with is what we have at the bottom here. The temperature of a given point, xi, yj, equals a quarter of each of those neighbouring points. What it basically means is the temperature in the centre on our diagram here, marked in red, is the average of the four neighbouring temperatures. So if we were to think of this as a simultaneous equation, the temperature at the centre point equals these four temperatures added together and then divided by 4, or the average of those four temperatures. Now that's exactly what we're going to do in our practical example. For each of those nodal points, we're going to look at the four neighbouring points and we're going to set up equations in order for us to determine the temperatures at each of those given points after a certain number of iterations. So let's return to our example. And what we have in our example is we have a square plate. We know that the temperature at the left-hand boundary, the bottom boundary and the right-hand boundary is 0 degrees, and we know the temperature at the top is 100 degrees. What we want to determine is the temperature at each of these points, labelled T1 to T16, using our finite difference approximation. So first of all, let's look at what we know. We know that the temperatures at each of our bottom points here is 0 degrees, because they all sit on that bottom line. The corner cells, T1 and T4, sit on two boundaries where the temperatures are 0 degrees C. So therefore, we know that T1 to T4 are all 0 degrees C. I'm going to input those now, and I'm just going to input those as raw values because those values aren't going to change at any point during the iteration. If we continue to the second line, and again I'm just going to input what we know and what doesn't change first of all, T5 is also going to be 0 because it sits on that boundary where the temperature is 0. And T8 is also going to be 0. It sits on a boundary where the temperature is 0 degrees C. So I'm going to put in T5 as 0. I'm going to skip T6 and T7 for now, and I'm going to input T8 as 0. If we continue to our next line, for the same reasoning, we know that T9 is 0, and we know that T12 is 0. Again, I'm going to leave T10 and T11 for now. But when we move to the top line, we have T13, T14, T15 and T16. Now it should be evident that T14 and T15 are both 100 degrees C because they both sit exclusively on our top boundary. but T13 sits at a junction between a boundary where the temperature is 0 degrees C and 100 degrees C. So we need to take the average there. T13 is going to be 50 degrees C. By the same reasoning, T16 is also going to be 50 degrees C. It sits on a boundary between 100 degrees C and 0 degrees C. So now let's transfer that information. We've said T9 is 0, down here in the bottom left. We've said T12 is 0. We've said T13 is 50. T14 is 100. T15 is 100. And T16 is 50. As you can see there, I've highlighted T6, T7, T10 and T11 because we don't yet know what the temperatures are at those points, and this is where the iteration process comes in. Let's begin with T6. If we look at T6, we know that the temperature there, using the finite difference equation, is going to be an average of T10 plus T7 plus T2 plus T5, or it's going to be those four temperatures divided by 4. Now I'm going to input a formula into the second iteration box, and the reason behind this will become clear in a moment. So the formula that I'm going to input is equals a quarter, 0.25, times open brackets. Now the quarter here is because we're going to add the 4 values and divide by 4. So with having the quarter outside the bracket, I now just need to input my 4 surrounding temperatures. Now T2, first of all, neighbours T6, but T2 has a value of 0, so I'm not going to input anything in the bracket for that. T5 is also 0, so I'm not going to input anything in the bracket for that. T7, we don't know, but what we can do is we can cell reference T7. So we've got a quarter. T7 plus T10 is the other neighbouring cell. So again, I'm going to click on the cell for T10. Now notice I've clicked on the boxes for the first iteration. Now what we're going to do in a moment is we're going to assign initial values to T6 and T10, and then all subsequent calculations are going to look at that first iteration and then improve the calculation of the solution as we converge towards a final solution. I'm going to do the same for point 7. Now point 7 is the average of T3 plus T6 plus T8 plus T11. So I'm going to type equals, again it's a quarter, times, open brackets, T3 is 0, we need to add T6. Now for adding T6, I'm going to click the box that corresponds with the first iteration for the same reason as before. So we've got T6 plus T8, which is 0, plus T11, which I'm going to cell reference again. So we've got plus T11. So it's the average of those 4 cells. When we come to T10, our equation is a little bit more complicated, and you'll see why in a moment. T10 is surrounded by T6, T11, T9, and T14. And we'll take each of these in order. We have equals a quarter times. Firstly, we have T6, so I'm going to cell reference T6. Then we have T9, which we know is 0, so I'm not going to add anything in for T9. Then we have T11, which I'm going to cell reference. And finally, we have T14, which we've already said is 100 degrees. Now I need to include this in my calculation. The only reason I didn't include T9 was because the value was 0. Adding 0 would have had no impact. But I need to include it here for T10. Now finally, for T11, we have equals 0.25 times our surrounding points. Our surrounding points for T11 are T7. So I'm going to click on the box for T7 because we don't know its value. T10, we don't know its value. T12 we know is 0, so I don't need to add that in. And T15 we know is 100, so I do need to add that one in. So plus 100. Okay, so we have our formulas set up. What we haven't yet done is assign initial values to T6, T7, T10 and T11. Now, as each of those are relatively close to our 0 degrees C boundary, I'm going to begin by assigning each of those as 0 degrees C. Like so. We've already said the values of T1 to 5 never change, so I'm going to copy those across for 10 iterations. They just remain fixed. We've said the same for T8 and T9. And we've said the same for T12 to T16. So let's copy those across. We know that for T6 and T7 we have a formula in these cells, so I want you to see what happens when we paste these across. Now, at the moment, these values don't seem to mean anything, and the reason for that is because each of those are actually connected to T10 and T11 as well. Recall that these are simultaneous equations, they all relate to each other. So now when we paste these ones in, what we see is that we have values which begin converging. So T6 and T7 are both equidistant from the boundaries, so we would expect those values to be the same. After the third iteration, those values are both guessed or approximated as 6.25, moving to 9.4, 10.9, 11.7, and what we see is that that value begins to converge at around 12.4. If we're not entirely happy that we've reached a converged solution, what we can do is copy our cells along a little bit further. So 11, 12, 13, 14, 15 iterations, however many we deem to be necessary. And what we can see is that the temperatures, T6 and T7 are converging at 12.5, and the temperatures T10 and T11 are converging at 37.5. So if we refer to our diagram, we know we've got a temperature T6 of 12.5, a temperature T7 of 12.5, a temperature T10 of 37.5, and a temperature T11 of 37.5, using the finite difference approximation of the Laplace equation. We could go one step further. Knowing these four temperatures here, we could pick a point in the centre, or the centre of the plate, and we know, using the finite difference formula, that the temperature there would be the average of the four neighbouring cells. If we were to take the average of T6, 7, 10 and 11, the average comes out to be 25 degrees. Now this supports what we would expect, because if we took a point at the centre of the plate and we looked at four neighbouring points that would be on the outside edges here and here, and on the outside edge of the top and bottom surfaces, the average comes out to be 25 degrees. Now what we're going to do in the next part of this video is we're going to increase the number of nodes. We're going to repeat the calculations and iteration process to get a better understanding of the distribution of temperature on this plate. So earlier in this video we took the problem that we have in the top left hand corner here, and we divided our region into 16 nodes. What we're going to do this time is we're going to divide our region a little further, and this time we're going to divide it into 25 nodes as shown. Now the process that we're going to follow is exactly the same, so if you're unsure what we're doing here, please go back and watch the first half of this video. There's going to be a lot more simultaneous equations generated here, hence in practical terms the computation time would be greater. We won't notice it so much here, but if we was to apply this thinking to a finite element analysis model with millions of nodes, we can appreciate that adding more nodes increases computation time. So to begin how we started before, we're going to assign temperatures to nodes where we know the temperatures of those nodes are fixed. So to begin with, we can see that the temperature of nodes 1 to 5 is 0 degrees because they sit on the bottom boundary, and the neighbouring boundary is also at 0 degrees. So we have 0 for each of these cells. T6, or position 6, also sits on our left-hand boundary, and our left-hand boundary here has a temperature of 0 degrees. I'm going to continue up that left-hand side because we can see that nodes 11 and 16 are also at 0 degrees. But we need to take a little bit of care when we get to the node in the top left-hand corner, T21. That node there sits on two boundaries. It sits on a boundary at 0 degrees, but it also sits on a boundary at 100 degrees. We therefore need to take the average of those two temperatures and assign T21 a temperature of 50 degrees C. So T1, 50. Okay, let's return to the top and do the right hand side of the shape. We know that T10, T15 and T20 are all going to be 0 because they sit on that boundary. So T10, 0, T15, 0 and T20, 0. Now the top right hand node, T25, is also going to be 50 degrees for the same reasons discussed previously for T21. We're just left with a couple of points to define here. We have our top rows or our top nodes, 22, 23 and 24, and the temperatures of each of those are going to be 100 degrees C as we would expect. They sit on the 100 degrees C boundary only. So 22 to 24 are all 100. So I'm going to assign initial values to our central nodes. So T7, 8, 9, 12, 13, 14, 17, 18, 19. Now because all of those nodes are relatively close to a 0 degrees C boundary, I'm going to start by assigning them a temperature of 0 degrees C. I know they're not going to be 0 degrees C because they also have proximity to the 100 degrees C boundary, but this is an ideal starting point, and when we conduct our iterations we'll get closer and closer to the true solution. So let's start with these as 0. And I've highlighted each of those in yellow so that we can identify them easily. For those values that we know aren't going to change, I'm going to copy those across now, just to help to isolate the values where we need to input formulas. And I'll just do this for the first 10 iterations to begin with. Like so. But for our central nodes, we're going to need to construct some simultaneous equations to determine the temperatures. And we're going to do exactly the same as before. We know that the temperature at point 7 is the average, so a quarter, multiplied by the temperatures at the 4 neighbouring cells. Well, the cells neighbouring T7 are T2, which is 0, so we're going to leave that out of our formula. We could just as easily add 0 plus, but that's not necessary. T6 is 0. T8 is an unknown value, so we need to click on the first iteration cell for T8. And we need to do the same for T12, the 4th neighbouring node. Close our brackets and hit enter. Let's repeat for T8. T8 has T3 as a neighbour, or T3 has a temperature of 0. So we're going to leave that one out. But it also neighbours T7, so we need to click on T7. It neighbours T9, so we need to click on the cell reference for T9. And that's the temperature at our first iteration. And then T13 for T8. So we click on that cell. Let's repeat for T9. We've got equals a quarter times the neighbouring cells added together. So we've got T4, which is 0, but we need T8 plus T10, which is 0, plus T14. So we're going to use our cell reference for the first iteration for T14. Okay, let's repeat this for the next unknowns. We've got T12, which is an average of the following: 0, T7, T13 and T17. T7, T13 and T17. Okay, for T13 neighbours T8. Now notice we've got no fixed boundaries on this one, so we're going to have to input a cell reference for each of our temperatures. We've got 0.25 times our 4 neighbouring cells here are T8, T12 T14, and T18. And next we move to T14. And the cells surrounding T14 are T9. So we click on T9. T13. Then we have a fixed boundary of 0 at T15. So we'll leave T15 off. And finally T19. Okay, moving on to the top row, we have T17. Well, T17, if we look at our diagram, neighbours T16, which has a fixed temperature of 0. It neighbours T22, which has a fixed temperature of 100. And it neighbours T12 and T18. So we have T12 plus T18 plus 100. So equals a quarter times, open brackets, T12 plus T18 plus 100. Now T18 in the centre neighbours T13, 17 and 19, and T23, which has a temperature of 100. So we've got the average of T13, T17, T19 and 100. So equals a quarter times T13, T17, T19 and 100. And finally T19. T19 neighbours T14, T18, a value of 0 for T20 and a value of 100 for T24. So we have the average of T14, T18 and 100. T14, T18 and 100. Okay, so now we're ready to copy each of those formulas across for our 10 iterations. We notice when we copy the formulas for T7 to T9 across that those values remain at 0, but that's because we haven't taken into consideration the changes in T12 to T14. Now we see some changes occur, but they're also both going to relate to T17 to T19. So when we copy those across, we're going to get a more complete picture. Now, what I want you to notice here is that T7 and T9 are the same, as are T17 and T19, as we would expect, because they're equidistant from the boundaries. But what we can see at this present time is that we don't have convergence of those values. From iteration 9 to 10, we've got a value that's approaching around 6.5, but we haven't carried out enough iterations to be certain that that's our value. We see the same with each of our variables. Because we've got more equations, we need more iterations now. So what I'm going to do is I'm going to copy all of these along. Okay. Now what we can see is we have got convergence in those values. T7 is converging at around 7.14. T8 is converging at 9.82. Again, we have 7.14 for T9. T12 and 14 are converging at around 18.75. And right at the centre, T13 is converging at 25 degrees C. Now that's exactly as we would expect from the previous example. That's the temperature at the centre of the plate, which directly relates to the temperatures at the boundaries if we just had one node in the centre. And we see convergence for our temperatures at the top, T17 to T19. Okay, so we can see that more calculations are required if we increase the number of nodes. So therefore, what are the benefits? Well, previously, we only knew the temperatures at 4 points within this geometry. So although we had an idea of how the temperature was spread throughout that plate, our information was relatively limited. Now we know the temperatures at a lot more points, so if we were to produce a temperature field, it would be a lot more accurate because it would be based around a lot more data points. So we have the downside of increased computation, but we have the upside of improved accuracy. The other thing that is important to note here is that this method only works if each of the nodes are equidistant, like we see here. If we had a triangular mesh, or we had areas where the mesh was more refined, then what we have to start to take into consideration is the distance between the nodes as well as the temperature of those nodes. So the calculations become even more complicated. However, that said, what this does demonstrate is that using more mesh elements, although it does lead to greater computation times, does enable us to gather more information or more accurate information about the distribution of temperature within that plate.